Now let us look into another examples to calculate the short-term losses. Based on the pulse tension being given here, calculate the short-term losses. The details are given here. FCK equals to 40 Newton per mm square. The modulus or elasticity of the steel tendon is 195 gigapascal. T equals to 3 days. Cement type R being used. A total of 8 units of 7 wire standard strength with the diameter of 15.2 mm are used. The total pre-stressing force is 1200 kN. The clear span of the beam is 12 meters and the eccentricity at the midspan is 450 mm. The tendon profile provided in these sections is as indicated here. There will be no eccentricity at the end of the beam and the midspan eccentricity will be equals to 450 mm. Assume K is equal to 0.008 and the tendon is stressed successively. You may pause the video for a while for you to work out the solution. To solve these questions, first you need to identify the short-term losses related to the section. It is a pulse tension beam and the tendons are stressed successively. This gives you a situation that all the 3 short-term losses are required to be checked, which include the elastic losses, frictions and wobble, and also drawing of the wedges. Based on this slide, the elastic losses for the pulse tension member, these equations will be used. With that, we will need to find the relevant parameters in order for us to compute the losses. Within the equation here, there are components of the steel tendon, concrete, and also geometrical properties and stresses. Let us find them one by one. First, we determine the ECMT here, which is given by the equation here. To do so, we need to find the ECM, FCM, and also FCMT. The FCM can be determined from the formula here. The concrete strength is 40. That gives you FCM equals to 48 Newton per mm square. Substitute this 48 Newton per mm square into the equation here. You get ECM as listed here. Next, you need to determine the S value here. Referring to this table, type R is being used. S will be equals to 0.2. The T now is equals to 3 days. Substitute the relevant value into the equations. You get FCMT 31.8 Newton per mm square. Substitute FCM, ECM, and SCMT into the equation here. You get ECMT here. Modulus or elasticity of the steel tendon is 195 gigapascal. The total steel area will be equals to 1112 mm square. And the geometrical property of these sections is calculated in the previous example. The N now is equals to 8. The sigma C will be equals to 13.7. This is obtained by substituting the P, A, E, and I into the equation here. And substitute all the relevant value, you obtain the losses equals to 41.8 kN. In terms of the percentage out of the total pre-stressing force, which is 1200 kN, it is about 3.5%. Next, we calculate the frictions and wobble. The equation used is this. The effective span is 12 meters. The data here refers to the difference between the maximum eccentricity and the minimum eccentricity at the midspan and at the support. which is equals to 450 mm. The mu here refers to the table. Assuming that the tendons fill half of the duct, the coefficients of frictions will be equals to 0.19. The K is given, which is equals to 0.008. In this equation here, you need to find the theta. The theta will be the summations of these two, which means that this minus this. To determine the gradient theta 1 and 2, you may use these equations. The theta here is 450. The L here represents the total length of the span, which is 12 meters. And the X here refers to the X1 and X2. X1 consider as equals to 0 and X2 consider as 12 meters. Then we obtain the gradient here, and the X here refers to X2 minus X1, which is the span of the beam, 12 meters. Substitute all the relevant value into the equations. You get the total loss due to the friction and wobble, 90.3 kN. In terms of the percentage of the losses out of 1200 kN, 7.5% of losses occur. Next, you need to calculate the drawing of wedges. Based on the slide here, these equations will be used. You will need this P, which is the frictional loss per unit length. Since that we have calculated this previously, whichever value obtained from here will be divided by the beam span. That gives you the P equals to 7.525 kN. Next, we need to calculate the L here, which is in the functions of the drawing, area of the steel tendon, modulus of elasticity, and also the P. Assume that the drawing of the wedges is about 6 mm. Substitute this 6 into the equation. This represents the total area of the steel tendon, and having all the value substituted into the equation, you get L equals to 13.1 mm. And the total loss will be about 197.2 kN due to the drawing of the wedges. The questions asks us to determine the short-term losses of the section. That means you will need to sum up all the three types of losses for short terms. These summations will give you 329.3 kN, which is about 27.4%. If you can remember the examples that we did long time ago, the alpha was assumed to be 10%. This final calculated answer is significantly larger than this. That means the checking based on the assumptions of the alpha equals to 0.9, which was found pass for the serviceability limit state, is now no longer valid. You will need to use the exact losses here for you to redo the stress limit check again in order to confirm the sections pass. This is a very significant process which you cannot omit when the actual losses is very significantly different from the assumed value. With that, you will need to redo the analysis here based on the PE tendons profile proposed and use the appropriate value of the alpha and beta. Then you check one more time for the stress limit. If the section pass, then you know that the section will be safe. If the section fail, it is either for you to change the geometrical property of the section or change the P and E, or even try to work out some mechanisms to reduce the losses so that the actual losses and the assumed losses are not significantly varies.